Okay, our final speaker of this session is Lester Mackey. He's a statistical machine learning researcher, and we're lucky enough to have him right here in the area at Microsoft Research New England. He was previously full-time faculty at Stanford in the statistics department, also affiliated with computer science, and he maintains an adjunct position there today, and we're excited to hear him speak.
Thanks, Tamara. Thanks to the organizers for having me here. Is there a clicker I should use for slides? Great, so I thought I would use my time today to tell you a story. This is a story of machine learning, of climate, and of the Wild West. And before I jump into that, I just want to acknowledge my excellent collaborators, Jessica Huang and Paula Orenstein. They're PhD students at Stanford, Judah Cohen and Carl Pfeiffer at Atmospheric and Environmental Research, and Ernest Frenkel, who's right here at MIT. So my goals for this story are fourfold. I want to bring some awareness to this important problem for water management, subseasonal forecasting. I want to give you an example of crowdsourced science, and this is, in this case, the Subseasonal Climate Forecast Rodeo. I want to point you to a really rich data source that we've developed called the Subseasonal Rodeo dataset, and I want to highlight some effective machine learning tools for tackling this sort of problem. So the story begins with this guy, Judah Cohen. He's a climatologist, and he's the director of seasonal forecasting at Atmospheric and Environmental Research. And one day he came to me and said, "Lester, I have a concern. I'm concerned that the community is not making the best use of historical data in weather and climate forecasting. Instead, the predominant paradigm is what's called numerical weather prediction, which is essentially a purely physics-based model of how the atmosphere and oceans evolve over time. So here's a cartoon of how NWP, numerical weather prediction, works. So you essentially you initialize your model with your best guess at current weather conditions. That's an inference that you have to make. And then you simulate future weather by discretizing partial differential equations that govern how the atmosphere and ocean evolves. And you do this using supercomputers. All right, and so there's some limits to this, and those limits largely come from the chaotic nature of this process, of these equations, actually. So errors in your inputs, any errors that you have in your initial estimates of the conditions, rapidly amplify, and provably, this whole process breaks down around 14 days. So this won't really work well deterministically more than 14 days out. And Lorenz proved this some time ago. And so what can we do to get around this? Well, there are a couple of things that people will do to get around this. One is to ensemble. So I can actually fit my model with different initial conditions and with different model parameters to capture the uncertainty. I can average across those different predictions, and that improves my estimate somewhat. And another thing that's done is what you might call debiasing. So actually comparing the predictions of these models to what actually happened in recent years and subtracting the means, removing the bias. But to a large extent, that is the extent to which historical data is going into these forecasts. And that's not a very great degree of historical data utilization. Okay, so we'll come back to that in a moment. So that was concern number one. And then he said, "Lester, I have a second concern, and I think that my concern is that subseasonal forecasts are especially poor." So to unpack what that means, I think we need to understand a little bit about how meteorologists look at forecasts. So I think the forecasts we're most familiar with are weather forecasts, and those are pretty short term. So those maybe go out to about 20 days, and typically you're not trusting them if they've gone out to 20 days because they're not that good. So maybe a day out or so, they're quite good. By the time you've hit the end of a 10-day forecast, they're not that great any longer, and that's the extent of what you might call weather forecast. On the other end of the extreme are what you might call climate forecasts. These are predictions over months or seasons or years or even decades. Typically, our forecasts for climate aren't as good as they are for short-term weather, but we do get a gain in skill. Skill is, what we'll call accuracy throughout this talk. That's what it's called, accuracy in the meteorology community. And you get this gain from simply from the fact that we're averaging over longer periods of time. So if I want to make a prediction over years, that's a less noisy prediction than what's the weather going to be like tomorrow. Okay, and so that's what this big bump up from skill comes from. But then there's this period in between, lying at the boundary of weather and climate, And that's called the subseasonal regime. That's about 2 to 6 weeks out, and typically you care about predictions averaged over 1 or 2 weeks. This is considered to be a particularly difficult regime, in part because these forecasts depend both on the initial conditions that impact weather and on the global conditions that impact climate, and because because they have a finer granularity than typical climate predictions, you don't get that big bump in skill from long-term averaging. Okay, so subseasonal forecasts, he said, that's where we should focus our efforts if we want to make an impact in this community. So subseasonal forecasting, what and why? For the purposes of this talk, for the story, I'll say subseasonal forecasting is predicting temperature and precipitation 2 to 6 weeks out. And then you might ask, why do I care about predicting this? And there are a variety of reasons, and I'm listing some of them here. These forecasts have applications in a lot of different domains. So allocating water resources is one of the big ones, irrigation water for farmers, water for hydroelectric use, managing wildfires, preparing for weather extremes like droughts and floods. There are other applications to crop planting, irrigation scheduling, fertilizer application, and energy pricing. But Judah said to me, if all of this is not motivation enough, there's also this poster that he brought to me, which says, saddle up for the subseasonal climate forecast rodeo, $800,000 in prizes. So I thought, okay, that's interesting. That's a weird poster. So let's try to unpack some of what's on this poster that Judah presented. So to understand that poster, you need to understand what the US Bureau of Reclamation is and does. And so I've given you a mission statement here, but I'll basically say that the US Bureau of Reclamation, it's a government agency. It manages water in 17 western US states. The western part of that mission is where the Rodeo part of that poster comes from. Okay. And what does it do? So it provides water to 1 out of 5 Western farmers, irrigation water for 10 million farmland acres. It actually is, I think, the second largest hydroelectric power producer in the US. And they put out this poster. They started a contest around subseasonal forecasting, and a big part of the motivation is what I highlighted in red here. And it says that during the past 8 years, every state in the Western US has experienced drought that affected the economy both locally and nationally. And they want to be able to anticipate this sort of thing so they can prepare locally and nationally. So what did they do? They started a contest. It was called the Subseasonal Climate Forecast Rodeo. It started in April of 2017, ended last year. It was a year-long, real-time subseasonal forecasting competition, and it was designed to advance science, to raise awareness about this problem, and also to provide a platform for evaluating these sorts of forecasts. And it was done in partnership with a number of other government agencies. Okay, so how did the rodeo work? Well, essentially there were 4 separate forecasting tasks. There were 2 variables that you were trying to predict, average temperature and total precipitation. And there were 2 different outlooks. So in weeks 3 to 4 from now and in weeks 5 to 6 from now, those are your 2 outlooks. And together it leads to 4 forecasting tasks. And the forecasts that you were making were issued on a 1 by 1 degree latitude-longitude grid across the western US. So the blue dots are the points at which you need to make forecasts, and in total there are 514 of those points. I'll call that G for the talk. Okay, and you have to do this every 2 weeks. And so the contest started April 17th, ended May 3rd. Just so you understand some of the rules of the contest, if you're disqualified, if you miss 2 of your submissions, this is very harsh. For instance, 1 submission was on Christmas Day. Several teams dropped out because of this rule. And then eventually, and so the way you provided your forecasts was in NetCDF format, which is a popular format for scientific data, and you uploaded it to a server, and your predictions were evaluated on that server. Okay. So that's the task. How are you being evaluated? Well, for that, we're going to need a little bit of notation. So recall that we're making forecasts every 2 weeks, and every forecast is over a 2-week period. So average temperature or total precipitation over a 2-week period. So each 2-week period starts on a date T. So we'll identify the period with that date T. I need to extract from that date the month-day combination. So if it's January 1st, 2018, the month-day combination is just January 1st. And on that date, you have the observed outcomes. This is a vector. It's a g-dimensional vector because you have one outcome for every grid point that you care about. Okay, so that's YT. Those are the observed outcomes, either temperature or precipitation. But we actually don't care about predicting the raw outcomes. We care about predicting what are called anomalies. That's the difference between the outcome and what you might have expected just based on recent history. So we're going to subtract away from each outcome what's called the climatology. That's the average temperature at that grid point on that month-day combination over a 20-year period. So I look at 1981 through 2010. I see like what was the average temperature at this location in January 1st, and I subtract that away from my outcome. And the difference is called the anomaly. And the anomaly is what we'll be trying to predict. That's a vector AT. Okay, so the way you actually measure the anomaly is the quality of your forecast is called skill. There are various things called skill, but this is one definition of skill. And it's essentially a cosine similarity between your predicted anomalies and the true anomalies. So it's just a measure of how the angle between the vector of predictions you made across the western US and the vector of truth across the western US. Okay, so this is a somewhat unusual objective function for machine learning, and it's also worth noting that it's a multitask objective function. It actually couples together your predictions across the US. A prediction you make somewhere actually influences your evaluation everywhere else. So let's just keep that in mind. All right, so that's the evaluation. And then what did you have to do to win this contest and get all the, those $800,000 in prizes that they advertised on the poster? You had to outperform two benchmarks just to qualify for prizes. The first is what's called a debiased climate forecasting system V2 forecast, CFS V2. This is actually an operational system developed by the National Centers for Environmental Prediction. It's what the US uses for these longer-term forecasts. The system itself is actually quite poor at making these longer-term forecasts, and that's where the debiasing comes in. And so the system is formed by averaging 32 of these numerical weather prediction forecasts with either different initial conditions or different lead times, and then debiasing them by looking at the difference between their predictions over the period 1999 to 2010 and looking at the truth over that period, and then just subtracting one mean and adding the other mean. Okay, and that actually makes a huge difference. And so that's one of the benchmarks. And the second benchmark was something they called damp persistence, and we never quite figured out what this benchmark was. They only had this vague description of developing regression coefficients somehow over the past. But you also had to beat that benchmark. Okay. So just to give you an idea of what different levels of skill look like, I thought I would show you a few pictures. So here are a few pictures. These are actual pictures from the competition. I picked out some ones where we did particularly well because it's, this is my talk, so. So in the top right, you see the truth. This is what was observed over this 2-week period. Red means, and this is for temperature, so red is hotter, blue is colder. And the top left is what we forecasted, and this was a good prediction. So this has a skill of 0.8383. So skills between actually -1 and 1. So this is good. And the bottom left, you actually see what one of the benchmarks produced. This is the CFSV2, the operational forecasting system. This is a pretty poor prediction. It has a lot of cold predicted where it should be quite hot. And that is a skill of -0.4. That's what a -0.4 skill looks like. It turns out that the damp persistence predictions were all so close to 0 that you often couldn't see them at this resolution on the map, so we'll just ignore that for now. Here's a second forecast. This is for precipitation. So the top right is, again, what was observed. Darker blue means more precipitation. Browner colors means less. And top left is our prediction, which actually is pretty bad. This is actually what essentially like a 0 skill forecast looks like. This means our forecast was essentially like orthogonal to the truth. Okay? And on the same task, CFSV2 again had a pretty negative skill. So this is a -0.2 skill type forecast. It's dry often where it should be wet. All right, so this just gives you a flavor of what these predictions and what skills look like. Okay. So, all right, so what about the data in this task? This is a forecasting challenge. You'd imagine there would be some data that we'd be using for forecasting. Actually, no data was provided. The real challenge was just to do whatever you want, somehow come up with forecasts. It could use data. It could just be based on your intuition. You might already have a forecasting model that you just want to test out. You could do whatever you want, upload your forecast, and they'll be evaluated. So there's no data. But of course, the organizers did identify what ground truth data they would be using to evaluate your forecast. So that's quite important. What is the ground truth temperature? What is the ground truth precipitation? But otherwise, you could just do whatever you want. You could even use existing physics-based models in your forecasts as long as you improved upon them. All right, so because there was no data and because we were machine learning people, we felt like we needed data. And so we created what I'll call the subseasonal Rodeo data set just by scraping lots of government websites and then standardizing them onto their common grid and at common granularity. And so we think this sort of data set is useful both for training up other forecasting models and for evaluating your forecast. So we've released it publicly through the Harvard Dataverse. And it has data from, it has temperature data and precipitation data, of course, but also geopotential heights, relative humidity, pressure data, Madden-Julian oscillation data, multivariate El Nino southern oscillation data. We even have some very coarse-grained model forecasts from numerical weather prediction models that we managed to get for free and somewhat consistently. And all of that's there in this data set. Okay. So, and what did we do with this? So what were the forecasting models? So we essentially took two different approaches and then ensembled them. And so I'll give you a very brief description of the two. So the first approach I'll call multi-LLR, so multitask locally linear regression. And the idea here is to incorporate lag measurements from all of those different data sources, so sea ice concentration and temperature and pressure and Madden-Julian oscillation, throw all of that in there, knowing that not all of those variables are going to be relevant for any given prediction, for any given forecast. For instance, in the summer, snow cover is typically not as relevant in the West. And so what did we do? So we threw all the measurements in. We had this multitask model selection procedure that would select features on a date-by-date basis to prune the irrelevant regressors and come up with a better forecast. That's a high-level view of that first method. The second method is quite different. We call it AutoKNN, multitask nearest neighbor autoregression. And the idea was that we wanted to identify dates in the past that looked most similar to the date that we're trying to predict. We did this by looking at past histories and seeing how well the history of dates in the past predict the history of our target date, taking into account that we care about cosine similarity as a skill measure. And once we've identified those dates, we use the observations of those dates as the features in our regression. So unlike the first method, this is actually only using temperature to predict temperature or only using precipitation to predict precipitation. So it's quite different from the other method. They actually typically had different strengths and weaknesses, and so our final step was to ensemble them together. It turns out that even though this cosine similarity is not a convex function, there's something like a Jensen's inequality that you can derive that would guarantee that if you ensemble in a particular way, in this case it's by L2 normalizing your anomalies first and then averaging, then the average skill is always going to be better. Sorry, the skill of that average is always going to be better than the average skill, provided that your skill, that the average was better than 0. Okay, so this is what we do. So let's see how this performs. So first I'm showing you some performance just from the contest period. This is a year-long period. Every 2 weeks you're making a forecast. At the bottom in the table, I'm showing you the average skill over that year for each of the 4 prediction tasks. And there are a few things worth highlighting. Each of the methods individually, so multi-LLR, AutoKNN, and the ensemble, outperform each of the benchmarks. So that's great. Even the simple method that just uses temperature to predict temperature, that outperforms the operational forecast from the US and the damp persistence. And then the ensemble in each of the 4 tasks also outperforms the top competitor for each of the 4 tasks. But it's worth saying that the competitors, so here I'm evaluating static systems. Over the course of the contests, every competitor had a system that potentially was evolving over time. So it's worth highlighting that. At the top, I'm actually showing you the distribution of skills date by date across the contest period. And the main thing I want you to take away from that, so each row represents a different method, and each column represents a different task, temperature or precipitation. So the main thing you should take away from this is that the benchmark methods typically had more extreme negative skills, and that's what really was dragging down their overall skill, much more so than the methods that we were proposing and evaluating. All right. So on top of the contest period, after the contest ended, we thought we should do a historical evaluation over other years as well. So we evaluated the methods in a rolling fashion over every year since the climatology period. So that's 2011 to 2018. And what I mean by rolling is that we only use data from the past to make our predictions. So in 2011, we throw away 2012 to 2018 and just use data from the past. And so what you see roughly is that, again, so at the top I'm showing the average performance over that entire 2011 to 2018 period. The ensemble in particular improves over the operational forecasts. It's by about 20 to 38% for temperature and about 120 to 146% for precipitation. That's the type of improvement we're seeing. And then we thought, well, we didn't actually have access, for some somewhat technical reasons, we didn't really have access to the debias, the fine-grained debias operational forecasts for training. But at prediction time, we can certainly acquire those forecasts and incorporate that into our ensemble. So I'm also showing you a three-way ensemble. What I'm calling ensemble CFSV2, the last column in this table, is a three-way ensemble between multi-LLR, AutoKNN, and the operational forecasts. And that gives a further improvement. So that prediction improves over just doing the operational forecast by about 37 to 50% for temperature and 128 to 154% for precipitation. The plots in the bottom are showing you year-by-year average skills of each of these methods. So the red curve is our ensemble, the blue curve is the ensemble with CFS added into the ensemble, and the green curve is the operational forecasting system. And what you see is that typically the ensemble is doing better than the operational forecasting system, but when it's not, ensembling that in as well gives you this boost that captures the benefits of both. All right, so I mentioned that this first method, this multi-LLR, is doing feature selection. And in fact, even though we're starting out with order 20, about 20 features per task, typically it only selects about 4 of those for any given date for precipitation and 7 for temperature. And what I'm showing you here is the frequency with which different features are selected for different prediction tasks. And what we found was that across all 4 tasks, pressure and lag temperature measurements were quite predictive and quite useful and selected most frequently. In precipitation tasks, we quite often selected these coarse-grained model forecasts that we had access to. They were much less useful for temperature, but they were very frequently selected for precipitation. And we think it's just that the precipitation skill is quite low across the board, and these coarse-grained model forecasts basically were about as skillful as anything else in that regime. You can also explore what sorts of neighbors were selected by this AutoKNN procedure. I said for a target date, we're trying to find dates in the past that are most predictive, that we think are most similar to that target date. So what sorts of dates are we picking up? And so what I'm showing you here is the month distribution of the most similar neighbors learned by AutoKNN for precipitation as a function of the month of the target date. So at the top, we have the months of each of the target dates, January through December, and at the bottom we have the months of the selected neighbors, the top selected neighbors. And there's a little streamer line going from the top to the bottom if you picked a neighbor from that month. And so one thing you can take away from this plot is that the top neighbor is typically from the same time of year. So summer target dates typically pick summer neighbors. Similar, for other seasons as well. Actually, interestingly, the same sort of trend doesn't hold for temperature. For temperature, we're actually picking dates all across the board. So if you're trying to predict the date in June, you might have picked a neighbor in January, you might have picked a neighbor in March. It was all over the place. But precipitation was much more structured in this way. For temperature, there are some patterns to the temperature of neighbor selection as well, though. So I'm showing you now the month of the top 20 neighbors for temperature by target date. And so in this case, we use 20, essentially we're using 20 nearest neighbors. That's why there's the 20 neighbors listed here. But you see some very vertical striations here, which suggests that the neighbor months tend to be pretty homogeneous. So even though my top neighbor for June might be in January, typically all 20 of the neighbors I pick are in January, which is interesting. And a similar trend holds for the year. Typically neighbors tend to come from the similar years. All right, 1 minute left. So great. So that's all I wanted to share with you. So this is the end. But if you want to learn more about this, we have a write-up called Improving Subseasonal Forecasting in the Western US with Machine Learning. And thank you for your time.
adding ensembles were helping in your setup. What if, I mean, clearly there's some structured way in which you want to add more ensembles, right?
Yeah. So I think, so I'd love to do much more. So what I presented was largely what we developed in the course of this year-long competition, and there are many other things we'd like to explore. Now I have the leisure to do that because we don't have this like bi-weekly deadline hanging over our heads. And I think you're right. I think ensembling was key here, and that could be exploited in a much more systematic way. And part of that actually is related to the fact that cosine similarity is a pretty unstable measure of quality. You know, if the magnitude of your predictions are small, a small perturbation in your predictions will lead to a very different similarity. And so I think the averaging has a big role to play there.
So how many contestants were there? How many people participated? And where is the money? Where did it go?
Where did the money go? Yeah, so I think, so in the beginning there were about a few dozen teams. Many of them dropped out midway through the competition. And so by the end of the competition, those who ended up finishing the whole year-long competition were typically those who were likely to win one of the prizes. So the money went in several places. So out of so about 4 of the teams at the end won prizes. So our team won a few prizes. First for temperature, 3 to 4 weeks. Second place for precipitation, 5 to 6 weeks. And then there were also prizes for historical forecasts. So first place for temperature historical forecasts. But a number of the other competitors, some of the other competitors were companies, like forecasting companies that were showing off their techniques. There was a father-son, a two-son team I think the father was already a meteorologist. The sons knew a lot about AI, so they came together to work on this competition. They did particularly well for precipitation. There was a radio station forecasting team that was participating as well. They did well in some of the tasks as well. Yeah, so I think in total, out of the 800,000 in potential prizes, they awarded about 525,000. Yeah.
Thank you for the talk. Maybe I missed that, but what was finally the top skill achieved by the best teams?
Oh, I can show you that. Yeah, so that actually was on one of the slides. Oh, here. Oh, it's maybe blocked by this. But the rightmost column here has the best skill achieved by the top team in each task. And you can compare that to the skill of the operational forecast and the dam persistence columns. So indeed, like a team did beat the benchmarks in every task.
Thank you. I wonder how generalizable your results are for global weather forecasting. Where are the sort of the challenges, and how do we sort of tackle them?
So that's something I'm hoping to explore this summer. First, we just want to extend it to the rest of the U.S. and then the Northern Hemisphere. A lot of what we're doing is quite generic, and so the methods will apply, and the question is, how will the skill vary? Certainly, some areas are much easier and have much less volatility than other areas. We don't anticipate any difficulties for the rest of the U.S. It'll be interesting to see what happens in other parts of the world. Some of the features that we selected were geared toward trying to predict the western U.S. For instance, when we looked at sea surface temperatures, we focused on particular seas, particular oceans. That sort of thing will be tailored region by region, but yeah, I'd love to roll it out for other areas and just see.
I think, unfortunately, we're out of time, but you should definitely feel free to ask all the speakers in the sessions more questions during the break, which is happening now. So first, let's just thank all of the speakers in the session.